Hi, my name is Yuqi Wang, a PhD student from the Institute of Automation, Chinese Academy of Sciences. This is the presentation of our paper, PanoOcc, Unified Occupancy Representation for Camera-Based 3D Panoptic Segmentation. Comprehensive 3D scene perception is crucial for the fields of autonomous driving and robotics. In recent years, vision-centric 3D scene perception based on cameras has garnered significant attention. In the past, 3D object detection based on monocular cameras often performed poorly due to challenges in depth estimation. However, recent advancements in 3D object detection based on multi-cameras, leveraging the fusion of different views and spatiotemporal information, have led to significant performance improvements. As a result, there has been a surge in research on 3D object detection and 3D semantic segmentation based on multi-camera systems. While BEV representation has shown promising performance in 3D object detection tasks, it still lacks the modeling capabilities for 3D scene structures. Compared to BEV-based methods, occupancy has two main advantages. 1. More general object representation, enhancing the ability to recognize unknown obstacles and irregular objects. 2. Finer-grained 3D scene modeling, incorporating height information encoding to construct realistic 3D environments, rather than just perceiving them in compressed BEV views, which is also more favorable for downstream decision-making and planning. Building on the advantages of occupancy, we introduce PanoOcc with two main motivations. Firstly, we aim to establish a unified output representation. Previous methodologies in 3D object detection, BEV semantic segmentation, vector map construction, etc., have focused solely on specific facets of scene representation, each employing its own format such as 3D bounding boxes or 2D semantic maps. Our goal is to explore a unified scene representation capable of uniformly expressing these tasks. Secondly, occupancy enables the unified modeling of foreground and background objects in voxel form. However, direct learning from 3D representations entails significant computational costs, and 3D space exhibits greater sparsity compared to 2D space. Hence, we emphasize two critical design principles in the feature learning process: coarse-to-fine learning and sparse computation. We introduce the model framework of PanoOcc, emphasizing the design of the occupancy encoder and occupancy decoder structures. Here is the comprehensive architecture of our approach, which takes multi-view images as input and outputs panoptic segmentation of the 3D scene. In the occupancy encoder, we employ voxel queries to transform two-dimensional image features into three-dimensional voxel features. In the temporal encoding layer, we utilize voxel points for temporal alignment, enabling the integration of information from historical frames into the current frame. For the occupancy decoder, we employ coarse-to-fine upsampling and explore the idea of layer-wise pruning to achieve sparse computation of three-dimensional features. This is because in actual 3D space, effective feature grids may only occupy 5% to 10%, making a significant amount of computation redundant. The task heads are responsible for learning object detection and semantic segmentation separately. Finally, the panoptic segmentation results are obtained through the refinement module. Experiments show that we achieved state-of-the-art performance on 3D semantic segmentation in the NUScenes dataset, approaching the performance of LiDAR-based approaches. Additionally, we are the first to achieve panoptic segmentation using a camera-based method. Here, we present a comparison between two samples processed by TPV-Forma and our method. Our approach enables the output of panoptic segmentation, particularly highlighting fine-grained instance discrimination. Our method is also applicable to 3D occupancy prediction tasks, achieving good performance on the OCC 3D NUScenes benchmark. Here are some visualizations of the occupancy predictions. As shown, the model takes panoramic camera views as input and outputs 3D semantic occupancy predictions for the entire scene. For future research, I plan to focus on two main areas. First, developing a general scene occupancy model for embodied intelligence, which is valuable not just for driving scenarios but also for perception in robots and other intelligent agents. Second, I aim to explore achieving 3D scene perception using self-supervised and unsupervised methods, eliminating the need for human annotated 3D voxel labels. Thanks for listening. Here is the link for our project. We also welcome a face-to-face discussion at our poster session.